let's get started. Okay, so yesterday we have seen Prim's and Kruskal's algorithm, and in Prim's we have seen the code with the adjacency list. The main difference between Prim's and Kruskal's algorithm is that they, even if they both are greedy, they are greedy in different terminologies. One is greedy on uh, node, I would say node and then distances, and another is greedy based upon the edges, the weight on the edges. So Prim's was that you start from a starting point, and then whichever is the least weighted graph or least weighted edge, you go there. Now Kruskal's algorithm says that okay, you don't have to start traversal from any of where, like just like there is no starting point, but we just have to find it out a graph or a pattern or a subgraph, I would say, in a proper way that covers all the nodes. So we just have to find it out the edges or the collection of edges such that those edges are connected so that it forms a graph and it covers every node. This is our specific need for minimum spanning tree. So what Kruskal's algorithm depicts that rather than starting from a vertices and then going forward with the help of weight of the edge, why don't we start with the weight of the edge as well? So this is a quick recap in which yesterday we have seen like in which way Kruskal's algorithm will work. It will work like we'll sort all the edges. We have all the edges. We'll create the object of it. We'll sort it based upon its weight. Once we have that, we'll take up whichever is with the least weight. So let's say AB is with the least weight. Sorry, not AB, it's an AD. So we have added AD with the least weight. After that, we'll mark as D as destination node, which has been covered. Then we'll add BE and we'll mark E as destination node covered. Post that in sorted order, CD is there. So we'll mark CD. Okay. And we'll mark C also as, because CD or DC, any one of them which is not covered as a source or destination, that we will mark as completed. Post that we will have to add AB. Even though starting point was A or the first node was AB, we will have to add AB. Why? Because so that so far with these three branches also, AD, DC and BE, we have covered all the nodes. If you see A, D, C, B and E, we have covered all the nodes with the three edges only. But minimum spanning trees rule is that it should have at least, I won't say at least, it should have exactly n minus 1 edge, where n is equal to number of nodes. That is the definition of a spanning tree. So that is not being covered over here. So we understood not only from the definition, but also from the visualization that this spanning tree is not connected. If you see, if I draw the spanning tree, it will be something like this. A is connected with D, D is connected with C, and B is connected with A. So it is disconnected two components. They are not a graph. They are two disconnected graph, right? This is one graph and another is another graph. So to create a spanning tree, which is a subgraph of the given graph, we have to add one edge such that this whole both are connected, and we can do it anyway. Like either we can connect AB, we can connect DE, or we can connect CE, anyone. But the least weight among all is of AB. So we'll add AB into the minimum spanning tree, and the final spanning tree which is getting generated is our final minimum spanning tree. Make sense? This was the quick recap of our previous algorithm that we have seen today. We have to see its code, right? So far clear with both minimum spanning tree and Kruskal's algorithm and this one.
Yes, Dhaval.
Yeah. We'll quickly see the code that in which way we can you know start writing the code, and then we can complete the what we can say Kruskal algorithm. So first thing is that what will be required. First thing is that we will need a priority queue, right? So that all the edges we can add into that based upon the weight. So if we have to alter the priority queues code to handle the weight on the edge, so that sorting will happen based upon the this, that we can do that. What is the next thing that we will need? The next thing we will need is resultant or the result set. So just like our previous logic, the result set still we will keep like this. The result set, we will have the object, and in result set what we will add, the parent child relationship, that this node is a parent of which node. So C will become, oh sorry, yeah, D will become the parent of C, and A will become parent of D. So we can understand that this graph is connected like this. In the same way, B's parent is A and E's parent is B. So in that way, the result set we will create, so that we know that which nodes and which edges are connected in which way. Okay, that is our two requirements. Okay, anything else that we would need?
Visited node just to keep and on edges.
Visited node, yes, that I have added for the logical part, so that I'll explain that in which way we should add or why we are adding the last age as well. But in code, it will not be needed. In code, it will not be needed. I'll explain you why. If you see, we can have the logic on the number of vertices, as well as the mathematical relationship is that if there are n nodes, number of edges will be n minus 1. So we can have this logic that until this n minus 1 edges we add into graph, we will not stop, right? So that we don't have to keep this logic, and that logic is still obscure if you see. And if I say how, then it is like this. The age that you will add will be like A to D. Okay, so you will say that okay, destination D has been met. Then if the definition is C to D or D to C, then based upon that it will be defined. If it is C to D, you will not add this age. Why? Because if the source of the age object is C and the destination is D, you will not add it. Why? Because the one destination D has already been done, right? So the age should be D to C. Now you cannot predefine. When you are creating a graph, you cannot predefine that, hey, which age will be this, either C to D or D to C, right? So that's why that logic will be very much complex to incorporate in code. So instead of that, we can go for such kind of logic in which we will add n minus 1 ages irrespective of anything else. And that is to cover all such kind of cases, as I mentioned, that two disconnected components it has created so far. So to avoid all that kind of thing, we will add n minus 1 edges. And that is mathematically proven that for minimum spanning tree, it's something like this, that if you're connecting three nodes, the edges between three nodes will be 2 if there are no multiple nodes and no multiple connections like this. And that is real as well. Over here also, if you see, the minimum spanning tree is like this. Each node is connected with one node only, in a way that they are in a line. If I show, or if I represent it in a very simplistic way, it can be like this, right? E, B, A, D, C. So if it is n node, number of edges will be n minus 1, right? And this is only called a spanning tree. This kind of a subgraph is only called spanning tree, where D To E, if you have to go, you have just one path, not like this, right? Not like this. This if this edge you are adding into the subgraph, then it is not spanning tree. The spanning tree will have only one path between any node to any node. That is only called spanning tree, the definition that we have seen so far. So that's why we understand that any spanning tree, if you represent, it will be represented like this, one line. Any node is connected with another node as an apparent child relationship only, right? A's child will be D, and A is a child of B, something like that. So there'll be only linear relationship, and because of that only mathematically we have this relationship n to n minus 1. If n number of nodes are there, n minus 1 connecting edges will be necessary. So with that mathematics only will go in code that until we add n minus 1 edges, we will not stop. Then our logic will be much easier to implement. Make sense?
Yes, Dhaval.
Okay. So now we will see the code. Then if you see, the coding part is very easy. Then in coding part, what will be necessary? One thing is that you create a priority queue and add everything into priority queue. Add every edges into priority queue, right? And then what you have to do? Then until, or I would say, like while n minus 1 edges you process, you just have to pull one edge from the priority queue. And what do you have to do? So let's say
Add
the
it in results.
yeah, add it into result set. So let's say A to D, I have found it out. Okay. So once I found it out, A is uh, A and D, what I have to do? Add it into result set. Now I think I forgot one case, which is like this. A minute. I think if it is A, it is B, it is D, if it is E, if it is like this, C. Okay, if it has one, 2, 3, 4, and 5. If it is like this, which all ages we will add into our code? We will add AB, let's say AD. So in minimum spanning tree, so it's minimum spanning tree based upon our logic I'm drawing. AD, then the next one is AB, then the next one is BE, the next one is DE. Now do you think this is the right approach, or do we have done any mistake? Are you getting my point?
Sorry,
Yeah,
Dhaval.
it's correct.
Okay, let me reshare. Let's say we have the graphs like this, the same graph but with a different weight on the edges I'm drawing. Let's say one, okay, and it has 2, and it has 3, and it has 4, and it has 5. Then which all edges I'll add based upon this logic? First I'll add AB in minimum spanning tree. Is that correct?
Yes.
Yes. Then I'll add AD in the minimum spanning tree. Correct. Now I'll add BE in minimum spanning tree because it has a weight 2 in increasing order, 1 1 2 3. So 2 I have added. And now if I add 3, this 3, am I doing any mistake? Yes,
Yes.
I'm forming a cycle if you see over here. And that is wrong. Minimum spanning tree, as we have seen so far, it is like with n minus 1 edges and n connected nodes, just like a linear relationship. It should, in visualization, it should get created. Over here it's not linear, it's in a loop. So here we are doing some mistake, right? So what can we do to avoid cycles?
Visited something which will remember what has been already visited.
I I I won't say I'm agree. Why?
Okay.
Because if you see in this case only, B and E both were visited, but still, and A is also was visited, but still we have added this age.
No, Dhaval. Actually, what I'm trying to say, for example, I'm considering the visited edges.
So see, this age is also not visited so far.
Okay, okay, sure.
First I have added this one, then I have added this one, then I have added this one too. But I haven't added so far this one. But once I add this into my minimum spanning tree, it violates the definition of minimum spanning tree.
Okay. The previous one, what you told, for example, A to B, then you are storing only B, not A. So in that case, if you are joining A to B, we are storing B. Then you are joining B to E, we are storing, sorry, according to the graph that you have given, 1, 1, 2, 3, 4, 5. In that case, what will happen? If you connect A and B, then I will store B. Then you will
Mhm.
add A and D, then I will store D. Then you add D and E. Then I will store E. And then after I'm getting 3 as E D. Then in that case, when I'm trying to add ED, then I will check the hash set that we already have D as visited. So I will not be connecting that.
Okay, that will be based upon the definition of uh, this thing. What we can say as in a destination. So over here you have marked as D as destination, right? Because the definition of age is ed, right?
Yes, Dhaval.
Right. What if the definition of age is de object, right? So you can mark, well, when you're constructing a graph, you can give this definition as well. De is a set. Then
Then it
then
will.
it exactly. So that was my point previously as well. When we have added a loop of n minus 1, this was the same logic we have discussed, and the same logic will be applicable over here as well, that we cannot rely upon the definition of an age, right? So what we have to do, we need to find it out some other logic. So let's say we have some logic via which we can find if there is a loop or not. We'll see in logic as well that how do we find it out the loop. But let's say uh, before adding this de age, we find it out what is the parent of d in minimum spanning tree. So in minimum spanning tree so far, or the whole graph, the parent of D is A, B, and E, if you see, and C as well and E as well. Now, if I'm adding E as well, okay, or I would say just in minimum spanning tree, if I add E as well, the parent of E will be D, A, B, and E. So if we are coming back to the same node, if you are starting from the D and we are coming back to the same node, like A to, after adding this age into minimum spanning tree, D's parent is A, A's parent is B, B's parent is E, E's parent is D. Because so far minimum spanning tree was this. Now if I add this age, then my minimum spanning tree will have, or D will have the same parent as it is. So if I find it out all the parents, we find the same node. And the same way for E, we find all the parents until we find the same node. And if that is way, we can find it out that, hey, then it is going into the loop, because loop means you will come back and result into the same node, right? So via this, if we can reach to a conclusion that if I'm coming back via finding a parent of a parent and then parent of a parent, and then I'm reaching to the same node, then this is this age, or adding this age into minimum spanning tree, is creating a loop in my minimum spanning tree. So I will not add this age. Got it? Can we think about such kind of an approach?
But
Right. Yeah,
yeah,
yeah, tell me.
actually, it won't be increasing the complexity. Miss. That's what I
Yeah,
was.
it will increase the complexity, but we don't have any other choice. As I said, we cannot rely upon the definition of an age. We cannot rely upon the visited one as well, like either source visited or a destination visited or both visited. That will rely upon the age definition. So on that also we cannot rely. So only uh, what we can say logical part on which we can rely is finding a loop that without adding de into resultant set, just we find it out what will be the loop or what will be the parent of any of the node. And even if you see just like this, let's say I'm erasing this, okay? This age is not added into minimum spanning tree, because if you once add it into resultant set, it will be difficult. Now find the parent of D. D's parent is A's parent is B's parent is E. So D's parent is what? E. In the same way, what is E's parent? E's parent is B's parent is A's parent is D. Now, via such kind of some relationship we can find, and we can understand that it is forming a loop, right? So if we find it out some way such that we can find it out that, hey, adding this age is giving us a loop, then we will not add this age itself into our resultant set. So DE we will not add into our resultant set, and then afterwards, which is the age which is into order 1 1 2 3 3 not we are adding, then 4, then we will add this 4C, and then we'll see that, yeah, now our connected components are complete and all the nodes are found as connected. Make sense?
Dhaval, is that I'm just thinking how to keep all the parents with respect to a particular node.
Yeah. So let's I think we have seen, but we can have a simple, let's say, give the number of indices like this: 0 1, CS2, DS3, and ES4. Okay, so let's say I have a normal array like this. So zero's parent is no one. Let's say, what is B's parent in a normal definition? That will be A, so which is like 0. D's parent, sorry, before that, index 2, index 3, index 4. So any one node I have to add it as an index, right? So whichever is not added, that I can add. So something like this. So let's say this is a parent array. So once parent is 0, then in the same way 2 is, which is C. 2's parent I can mark it as 3. 3's parent I can mark it as 1. 4's parent I can mark anyone. Let's say I'm marking 2. But the point is, with this kind of a definition, I can represent again this graph, not whole graph, but this relationship of ages I can, right?
Yes.
That who is the parent of this. So with such kind of a single array as well, I can create that who is the parent of which. And if you see, even if you add the fourth parent, matlab E's parent as C, D, or B, you can find it out if it is creating a loop or not. Let's say if you find it out whether D, C, and E are creating a loop or not, you can always find it out. Consider that you have just only this D, C, and E, three nodes into the graph. You can directly see that whatever the parent of E is, E's parent if you have defined C, and C's parent if you have defined E, then you see that there is a loop. Okay. Now, if E's parent you have defined C, C's parent you have defined D, and again D's parent in a unanimous way you have defined as E, you can see that there is a loop. So the point is, in any way you are defining, you can find it out whether you are coming to a same point or not. And that is a normal definition of a loop. Yeah. So we can have this kind of logic to find it out. If adding the age is getting us into the loop, then we will not add. Okay, so consider that we have such logic, something like this, that I'll find it out the end parent of any node. I have that logic ready, parent of any node. So if this parent, this logic I have ready, I can follow up this code. So let's go and write down that code, and then we will see what will be the logic for this. And with that, we will cover How can we find it out if there isn't a loop into the graph as well, right? Because we are, at the end, we are finding the loop into the graph only, right? So let's see if this definition and this definition do we have ready into the Kruskal's algorithm, then how can we find it out whether it is creating a, or whether our subgraph or whatever the given graph is there, its minimum spanning tree is what? Okay, so let's start understanding the code. So first thing, as we said, was the definitions, and the definitions will be looking like this. We will need all the ages. We will need priority queue. We'll add everything into priority queue. We will need a parent and child relationship in array, such that we can find it out who is the parent, who is the end parent of whom. Okay, we will see its code implementation later on. In some interview questions we can find it out, or the logic wise if you try it, it's an easy one. That is what we need. Another thing is final, we'll need the result set, and after that, until n minus 1 ages will continue on priority queue, and the 5.1 inside of that will check first of any age. Let's say age is xy. We'll find the parent of x, end parent of x, and y's parent, like this. And if we find it out that they both are same, that means it's in a loop. If it's a loop, do not add this age, else add this age into minimum spanning tree and continue. This would be our simple logic to implement Kruskal's algorithm such that we find it out the minimum spanning tree into our result set. Clear?
Yes, sir.
Yeah. Only the thing is that we need to find out what will be the code or logic for that such that we get this. Parent-child relationship, it's simple. But how do we implement this? Why? Because if there is an always a loop, you will go in finding out, or you'll go and complete the loop always. Like D's parent is A's parent is B's parent is E's parent is D's parent is A. Again, you'll go and in infinite loop and you will not return anything over here. So the implementation of this function is which we need to understand. But if you give a shot, it will be very much clear. When I have such kind of relationship, I just have to give any node's parent such that I'm not coming again and again on the same node. So even if there is in a loop, let's say D to A to B, B to E, and E to D, then again I'm going into the loop. So I'll not go into the loop in this code, okay? In this code of finding the parent, I'll stop at E and I'll say that yes, in the graph of this, the parent of D is E. Because after that, I'm going into the loop of D again. Like I'll be starting at the starting point again. And let's say if I want to start find the starting, the parent of E, what I'll do, E's parent is D, D's parent is A, A's parent is B, B's parent is E. So I'll stop at B. Got it? And I can say that, okay, now again, I'm going into the loop. So this is my parent, final parent. Now point is in which way, because if you see the D's parent is what? D's parent is A, B, and E. At the end, D's parent is E, and E's parent is what? B. Are they both same? No, they both are not same. So we will add this age, right? So the point is in which way we implement this logic of finding the parent that is necessary, and such that it should not give us, such kind of node, but what it should give, something like this. D's parent, it should give either E, and E's parent also, it should give either E. Then only then we can say that, hey, it is going into the loop, otherwise not. Or D is parent, we should get a D, and E is parent also, we should get D. Then and only then we can say that, hey, this is going into the loop. So we will see how do we implement this. But the core logic is that if the parent of both D and E are same, obviously it is going into the loop. And that's why we will not add DE into minimum spanning tree. So we'll see this logic later on. But right now let's understand that if this logic is already implemented somewhere, and that function do we have, if we have already, how can we implement the minimum spanning tree for Kruskal? And then we will see this logic. Clear?
Yes, Dhaval.
Yeah. So we'll see this part. So as you see, we have defined the Kruskal algorithm, we have defined the priority queue such that the comparator function is on the weight, because age object has source, destination, and weight. So the comparator is weight. After that, all the ages I'm adding into the priority queue so that we get the least one. Okay. Now I have a function make set, which will give me the parent-child relationship of all the vertices, so that I can find it out the loop easily with the help of this parent object. Okay. Now, final, which are the ages which I am adding into my minimum spanning tree? That definition I'm creating as an array list of age type, age object. Okay. Now what I'll have to do, as we have defined over here, once the definition is clear, the implementation part will be like this. Until n minus 1 ages I add, I'll not stop. I'll see whether adding this age is forming a loop or not. And if it is not forming a loop, increment my counter and add the age. So let's see that part. Until I add all the vertices into that. Okay, so it will be just based upon the definition of age only. It will be the same one. What I'll do, I'll find it out the parent of both source and destination. And if they both are same, if they both are same, we understand that it will create a cycle. As I said, it should give us like this, any of this. This function find should give any of such logic. Then and only then we can say that, hey, it is forming a cycle. If this is given to us, we can find it out that is it creating a cycle or not. If it is not creating a cycle, add that age into minimum spanning tree, increase the index count or the age count, that one age is done, second age is done. So this is like, this index is what? N, and until vertices minus 1, until n minus 1. So let's say this is I. So until I is becoming n minus 1, I'm doing it, right? Less than or equal to. So that what I'm doing is until n minus 1 ages I add, until that time I'm incrementing my counter. So after n minus 1 ages are added into minimum spanning tree, will stop. And this union is what? I'm just creating a parent-child relationship into minimum spanning tree and showing that the X is a parent of Y. That's it. Okay. So finally, I'll have minimum spanning tree into this one. Got it? We will see the find parts understanding and the union parts understanding later on. But so far, if these functions are given to us, is it clear? There are many other implementation of what we can say, this Kruskal's algorithm and Prim's algorithm as well. Okay, based upon, let's say, how we are finding the loop, how we are finding what we can say, ages are creating a loop or not. Also 2D metrics, with the help of 2D metrics, are we implementing the graph or not? So there are many variations of that. You can see that. Uh, you can read about those on internet, but the final goal is that we should get the minimum spanning tree. And the understanding of this, why I have added this only implementation, is that so that we can cover this logic such that we can find it out whether the graph is creating a loop or not. We will see that Okay, so that we can cover that part as well, that because in interview sometimes there's a well, I have seen that this question can be asked. Well, generally whenever I have given interview, generally people doesn't ask graph question, but there are 3 to 4 questions which are very much you know, people are likely to ask, and they are this: find a graph, find a loop in a graph. Second, that is that find coloring in a graph. With how many minimum number of color you can color the whole graph such that no two adjacent vertices have same color. Third thing, find a bridge in a graph. You know about what is a bridge in a graph, right? If you have graph like this, then there is no bridge. But yeah, there is a bridge actually. Yeah, there is no bridge. But let's say if you have graph in such a way that if you remove that edge, then the whole graph is divided into two component, then it is called a bridge. So find a bridge in a graph. These are a typical few graph questions. Then there are some of the implementation level questions, like there is an alien dictionary. Then there is um, ordering wala question. So ordering means which node should be completed after which node, like that. It's called sort. Which sort I forgot. Okay, so these are the few questions on based upon the implementation of the graph as well. So we'll see all, but as it covers the loop part, I have taken this implementation. Clear? Is it? Or is the Sunday blues? Harsh, Jose, Anurag, Rishi? So what I'm asking is that, okay, um, is because of these two functions unclarity, do we have some lag into the understanding of this whole Kruskal's algorithm, or something else? You can share with me.
Well, just one thing. This union that you have written
Hmm.
is because already in a single 1D array we are mentioning the relationships. Means mentioning the relationship in the sense we are mentioning the parent.
Yeah.
So in that case, is it necessary to write this union?
Yes, in a way, yes. Why? Because if you see a normal parent-child relationship, if you see the normal parent-child relationship we have thought was like this, simple, right? Now in that we have not added who is exactly the parent of who. In a way, like is parent can be defined as C or D or B, right?
Right.
Point is, if we have just defined C, okay, then we may not end with this graph only at D directly, so that we have to have such relationship in which the whole the parent-child relationship or such kind of thing is there. So what in union, what I would uh, have a logic such that along with this parent-child relationship, a normal single parent-child relationship, at the end, whatever the minimum spanning tree has parent-child relationship, that I keep on updating. That at the end, the D's parent, at the end, let's say if I do not add this, okay, age into my minimum spanning tree, at the end, D's parent initially is A, and at the end, I somewhere define that D's parent is also E. So if these two things I'm keeping, then so D's parent is A is defined over here, but D's parent is E at the end of the whole loop, let's say. If that thing is also I'm keeping a track of somewhere, then I'll understand that I'll not go into this loop ever, because I'm keeping the track of, or something like this, I would say. If you if you uh, um, if you want to understand it very clearly, what kind of union algorithm I'll try to add is that D has an apparent like A, B, and E all. So far, in my minimum spanning tree, we have added just these three ages, right? With the defined, let's say if it is 2, then, right, with this 3, and let's say this is 3 and this is 4. If this kind of graph is there, then in D, or for the D, we have only 3 parents: D to A to B, B to E, that's it. And A's parents are B and E and D, let's say. Got it? So in that way, I want to keep some relationship such that, not a single parent child relationship, but such that I find it out that if I add E, DE age, this relationship will be jeopardized. Why? Because then D's parent will be A, B, E, and then again D, right? If I add age ED, and that thing I don't want to do. So, so that kind of definition somewhere I'll keep such that it will be beneficial for me to find it out whether there is a loop or not. So what we'll do, the next question or next to next question somewhere, we'll take it up that find it out a loop into that, and we'll take the same algorithm of find and union. It is called a find and union algorithm. So we'll take the same algorithm, find and union, and we will see how this find and union will help us there. I think I should have taken this find and union before, but as it was together with Prims and Kruskal, I have taken this over here, and later I thought that find and union we will explain later on. And right now we can keep a concept that, okay, there is some algorithm of find and union, which gives us that does this graph, via adding this age, if we add this age in this graph, does it create a loop or not? If it doesn't create a loop, we'll go ahead and add it. If it creates, we'll not add it. So that's why I have added it, but no worries. We'll try to incorporate this question with the find and union properly. Properly in the sense with the code and all that things explanation. Then I think this whole part will be much more clear.
Yes, sir. And there will
Yeah.
one more thing.
Yeah,
If you have the, share it so that it would be helpful for us as well to see and understand how it is working.
sure. I think for this crucials I don't have. For prims I have added written down the code. I'll see and I'll edit. I think yesterday I forgot it, but I'll edit. Sure.
No problem.
Okay. So we'll take this, but today let's see if we have something else. So let's see few of the algorithms which are primitive, as say shortest path algorithm. What is the shortest path algorithm, and which are the type of those? Mostly you might have seen or you might have heard the very basic algorithm of shortest path is Dijkstra's algorithm. So we'll see what is Dijkstra's algorithm, what kind of logic he has thought for Dijkstra's algorithm, what kind of logic we have applied, so that we see a various kind of logic into graph, and then we go and solve some of the interview questions. Okay, so what is the shortest path algorithm? And if I define, first we need to define what is shortest path. So the path which is shortest it can be based upon two parameters, which is based upon the age and another is based upon the nodes. Age means based upon the weight of age. Another is nodes. How many number of nodes you are coming in between to reach to the destination from source to destination. If these are 5, let's say, then if you have such path where you have source to destination as just 2 nodes, then this is the shortest path, such like that. Or if it has a weight of 8 and 9, but this all have 1, 2, 3, 1, 1, then this is the shortest path. So based upon the definition of a shortest, the implementations can be different. But the Dijkstra's algorithm is focusing more on what? Weight. Because if you see in real-time applications as well, rather than number of hops or number of nodes into the graph, we more emphasize upon the weight. How much weight does this edge has? And based upon that, we define that whether this whole source to destination is shortest or not. So if I give you an explanation of that in terms of real world example, as I said, one thing can be Google Map, another thing can be uh, job schedulers or the workflow, as I said. So the age can define the time to complete this node, or the age can define that how many number of hours it can take to complete this job. So the point is, at every moment or at every level in industrial what we can say implementation, our main implementation is based upon the weight on the edge rather than the number of hops. Because one hope can be completed in 1 second, but another hope or another node can take 30 seconds, 50 seconds, 20 seconds. And based upon that, if we have to find it out something or such a path such that we complete quickly, that will be based upon the time. And time, sometimes we define it, not sometimes, always define it based upon the age of the weight. So majorly all the shortest path algorithms are defined as or on the weight of the edge rather than the number of nodes in the what you can say solution, right? So we'll see first what's the Dijkstra's algorithm and how can we go for implementation of it. And once we are clear, then we can see that, what kind of logical questions can be asked. As I said, one sorting question is there. Let's say topological sort, it says. Then what is the topological sort? Then second one is, as I said, finding a loop into that with union and find. How can we find it out that? Finding a bridge. So that type of interview questions we'll see once we complete this. Clear? Or if you want to switch to directly interview question, then also it's fine. Anything is fine. It's your choice.
I think we can start with this.
Sure. Obviously, this is a primitive logic, but still it will be helpful. So that's why I have kept it into the classes. Sure. So what Dijkstra's algorithm mention is that you can keep on mentioning or you can keep on traversing all the nodes from the source. So let's say you have source to destination, many of the path, right? I'll explain. Like this, let's say you have a graph like this, a traditional graph. You have all this edges and all. Now if you see from source to destination, you have many path. Now what Dijkstra's algorithm says is that to any node, let's say this has an weight 2, you go to A to B and you just mark that to reach to B from source. So that is clear that we are going to any of the node from source only. So from source to source, the weight is 0, but from source to destination, weight is 2. Right now you just mark it as 2. The rest of the thing which are unclear, they are infinite. That is what the implementation or the algorithm says for the Dijkstra. Then if you find another path to reach to the same node B via some other node, update this graph or update the rest of the graph. Let's see how. Okay, I'm just giving a gist, not the complete algorithm's explanation, but the gist is something like this. So let's say if these weights are, let's say 1 and 0, let's say. So when I update for C, I'll update 1 over here. That okay, infinite, initially the infinite is there, but now I went from here to here. So I'll say that okay, I can go from B to C. Sorry, I can go to A to C with weight 1. Now what I'll do, From B, I'll go to all the nodes which can be reachable. So from B again, all the nodes which can be reachable are E. So let's say its weight is X, its weight is Y. So wherever this D and E are there, I'll update that B's weight is 2 plus D's weight is 2 plus X and E's weight is 2 plus Y. It's lesser than infinite, so I'll update it. Now C is reachable with 2 plus 0 or 1, which is lesser? 1. So I'll keep 1 over here only. Now, when I start iterating from C, I'll check that C can be reachable. Via C, I can reach to B and D. Via C, I can reach to B and D, right? What I'll do, C can be reachable with 1 unit, and with 0 length or 0 weight, I can reach to B. So what I'll do, I'll update the B's value to, instead of 2 to 1, because from source to destination as B, I can reach via only 1 weight. 1 plus 0, 1. And C to D, instead of 2 plus X, I can reach plus 1 plus X only. Because let's say if C to D is also X. So I'll update it to 1 plus X. Now, over here, if you see, I have updated B's value, that B is reachable with 1 plus 0, which is 1 only. And initially, from B to I reach to E and D and I updated all the values. So I have to update if I'm finding some lesser weight or lesser amount to reach to some node and that has already been traversed, I again traverse it and I store it that, hey, not 2 plus X, but D can be reachable with 1 plus X and E can be reachable with 1 plus Y, right? So in that way, I'll keep on updating it. And in that way, if I go, then at the end, when I complete all the paths, I can find it out that, hey, what is the least weight or the sum of weights which can give me the path to reach to G. So what right now we just have to find it out. What is the weight to reach to from source to destination with how much weight we can reach. And then what we can do, we will see how can we print the whole shortest path as well. But this is the gist of the algorithm. Clear? This will be the gist of algorithm. Okay, let's get started with the same explanation that we have started. Over here, it will be just more clear with the slides and all that thing. So before that, I have skipped one part, that to find a shortest path, or you can also use breadth first search. So you can think about it. It's fairly simple, so I'm not explaining it. We can directly go to some algorithms which can be important. So let's go for that. So as I say, Dijkstra's algorithm says that traverse the node and keep on updating the distance. That is what the gist of the Dijkstra's algorithm is. And we'll see what is the logic. Let's see. Well, the gist I have given, but let's see the exact implementation or the exact logic. So the exact logic is that I keep this value somewhere. These are the definition of the nodes, like 0 is A, 1 is B, 2 is C, 3 is D, and so on. Okay, so henceforth, our graph will have 0, 1, 2, 3, 4 instead of A, B, C, D, so that in indexes, it can be very much easily identified. Second thing is that we keep on updating the distances, that from source node 0, which all nodes can be reachable via how much distance. So that we will keep on updating. Initially, everything will be infinite because right now I haven't updated anything. So whenever we find something lesser value, we'll update it. So everything will be lesser than infinite. So everything first has been updated with infinite. And this is a parent-child relationship kind of a thing, that this node is reachable via which node. So let's say B is reachable via A, then I'll make B's node's parent as A. So to keep that relationship, I'm just adding a spanning tree. array values. Okay, so these are the prerequisites for the Dijkstra's. Now let's get started. So let's say we have just identified all the values with a 0, 1, 2, 3, and then let's get started. So as everything is infinite, every rest of the things are infinite, and we are starting from the source, we see that it has two children's. So both children's distance, we will update it. So let's say for first node, the distance is 4. 0 to 1 you can reach via 4, so we'll update it and we'll mark that one's parent is 0. The same way, the next node, which is 2, and its value via which we can reach is 3, right? So that is what we have updated with this one. Now, the main core logic, which will come like this, and we will mark it as that this node is covered once all the children of that node is completed. Now the main logic is over here, that from any of the node, either 1 or 2, will start traversing the rest of the nodes. Let's say we are starting from the 2. So from 2 I can reach to 1, from 2 I can reach to 3, and from 2 I can reach to 4. So the same logic which I applied for 0, the same logic I'll apply it over here, that from 2 I can reach to 1 via one path. So 3 plus 1, 4 unit of path I can reach to the node 1. Is it lesser than already existing? No. Then I'll not update it. What if it's lesser? If let's say if it would have been something like this, 6 over here instead of 4, then this value would have been 6. Then I'll see that, okay, 1 is reachable via 3 plus 1, 4 unit, which is lesser than already existing 6, 1. Because in this case 6, the distance would be 6 initially over here. Then what I'll do, I'll update this value to 6, that one node is reachable with 4 unit of weight, which is the least so far, which is the least so far. I'll update, and I'll update the parent as well. That the parent of 1 will be 2. The parent of 1 will be 2, right? Clear? This is what we have seen in the gist. The same thing I'm explaining with the graph. Clear so far? Just for the first node, first two nodes. No response.
Yes, sir. It's
Yes,
clear.
clear.
Yeah, it's fairly simple. So, okay. So after that, let's say if it would have been 4 or anything, if it would have been 6, we know what to do. If it would have been 4, then we will keep it as it is. And the rest of the node values will start on updating. That from 2, 3 is reachable. 3 is reachable with 4 plus 3, 7 unit via making parent as 2. In the same way, from 2, D4 number 4 node is reachable as an apparent 2 with what we can say, uh, distance of 6, which is 3 plus 3, 6, and we'll stop there. We have covered only the second node, and all the nodes of, or all the children node of, or connected node of 2 are updated, which is pending from 1. 1 is pending. So then we'll start iterating on the 1. So zeros all the children are done. Zeros all children are 1 and 2. 2 is done. Now let's start with a 1. Now let's start with a 1. Now when we'll start with a 1, we'll start again. So far the distances are this, that this all nodes 0 to 2, 1, 3 and 4 can be reachable via this number of units of weight. When we'll traverse with 1, we'll see whether they are reachable with less or not. So we'll see that with 1, it can be reachable at 4 plus 2, 6. So if you see, the node 3 was so far reachable with 7 unit. 3 plus 4, 7. So then we will update it that, okay, 4 plus 2, 6, it can be reachable. So I'll update it with 6. And I'll change its parent. Previously its parent was 2. Now its parent is 1, and the unit is updated. That the node 3 can be reached with 6 unit. Now there is no other node which is untraversed, and that's why we'll mark it also as completed node or completely visited node, and we'll stop for that node. Now we will start for rest of the nodes which have come into the proximity of these three nodes. So for 0 everything is done. For 1 also all the nodes have been updated. For 2 also all the nodes are updated. Now for any of the nodes of the 0 and 1, sorry, 1 and 2, whichever the children node are there, from there we'll start. If we go by the indexing, normal indexing, we'll start with a 3. In just for loop, if we write down the code, it will be coming as 3. So we'll start from the 3, let's say. From 3 again we'll see that, okay, what is reachable? 5 and 4, and we'll see so far what is reachable, what is the what we can say distances or the weights so far, and if it is lesser than that we'll update it. So 5 is reachable so far with infinite. So first I'll update from 3 to 5. I can go with total weight. Total weight of 3 is 6. Total weight from source to reaching to 3 is 6. So 6 plus 1, 7. So that's 7. I'll update and I'll say that 5's parent is 3. 3, 6, and 6. Right? That is the first part. Then I'll update from 3. I can reach to 4 as well with 2 unit of time. So that will be total what? 4 plus 2, 6 plus 2, 8. And so far 4 is reachable via what? 6 only. So then I'll not update it. So finally my distances remains this, and 3's all children have been traversed. Then the next one I'll take one is 4. Once I take the 4th, again I'll start making that it can be reachable with 3 plus 3, 6 unit till 4. But once I start from the 4, from 4 I can reach to 3, and from 4 I can reach to 5. So 3 is reachable via 3 plus 3, 6 plus 2, 8. But it's already reachable via 4 plus 2, 6. So I'll not update it. Now 3 plus 3, 6 plus 6, 5 is reachable via 12 unit via 4. But so far it has been updated with 7, that it is the least one. So I'll not update it. If it would have been 0.5, then I would have updated that. The 5 is reachable via 6.5 via node 4. Via node 4. And then I'll mark that all the children of 4 are completed, and 5 itself is a destination node, so there we'll stop. Now once this table is ready, when all this both the arrays are ready, I can traverse my I can traverse my source to destination path. That the 5 is reachable with the least weight of 6.5 via 4. So my path is 5 to 4. 4 is reachable at the least weight of 6 via 2. Via 2. 2 is reachable with least weight of 3 via 0. Via 0. I reach to the source, completed it. Let's say this is not the case. Let's say this is not the case, and it was 6 only. Then also I can have the path. The node 5 is reachable with the 7 length with a 3. 3 node is reachable with the least weight 6 with the node 1. 1 is reachable with the least weight of 0, and we are done. If it would have been 6, then it would have been like this, right? This wouldn't be there. So with these two relationships, we can reach or we can find our shortest path very easily. So this is the shortest path algorithm of Dijkstra. Clear? The understanding of Dijkstra's algorithm, is it clear?
Yes, sir.
Now we'll see its code. Yeah, tell me.
Sir, you were saying yes.
Okay,
That's
you meant to say yes. Okay, so let's see its code. Now if you see the implementation, as I said, it can be in any way. Right now we'll see the easiest implementation of this. Dijkstra's algorithm will be with the help of, rather than age or we can say adjacency list, it will be easily with the adjacency matrix. Why? Because we directly can go to any weight or the age of weight directly, like what is the weight of 3 to 5 or 5 to 3? We can directly go to that value. So because of that, rather than traversing the whole adjacency list of 3 and all, rather than easily we can go so that we can access the weight quickly, like in order of 1. So that we'll go for the implementation of this graph as 2D matrix. Okay, not the adjacency list. Okay. So let's see that. So first we have distance array. We have the spanning tree array, as we have mentioned. It won't be spanning tree, won't be Boolean. It will be again integer, so that we can make the parent-child relationship easily. Okay. Initially, every spanning tree's distance is 0. That every node or any value you can say that okay, it's not reachable, and the distance is integer max. Then we can start that hook, which value to pick up. So initially for the source node, the value is 0. The source is index, like 0 is the index, like that. Okay. Now we will start iterating over the graph, and then we will make further logic. So what is our logic? That for all the graphs or all the nodes, we have to start iterating from the source node and update the spanning tree and distance, what we can say, values. And we need to use some other data structure for, like as I said, queue or heap or something else. Which one do we have to use for given implementation?
Queue. We can use the queue.
We can use the queue. Also, we can use some other techniques as well, but we will see that later on. And then we'll see the next part of it. Let's see. So right now, let's see that without using queue, if we can do that. Why? Because I have taken assumption that each and every node in terms of indexing, they are in like in 0 to n only, like over here in parent-child relationship, so that rather than I don't have to use queue. Okay, so without using queue, let's see that implementation. And that can be like this. For count equal to 0 to count less than v minus 1 until all the ages or number of all the nodes have been completed so far will go, because the last node will be the destination node. And I have assumed that in the same order of parent-child relationship, I have kept the numbering of the nodes so that I don't have to use the queue. Now, what I do, first I find the minimum distance between the source node and the given node. Got it? And that minimum distance, I'll update it into the graph if I do not have, so this is a spanning tree. This is a spanning tree. So if the spanning tree is unvisited, and
what is the given node level here? Minimum distance of distance comma source.
distance comma spanning tree I have written. The spanning tree in this sense, I'll find it out the minimum distance of the any node or from the source, what are the destination nodes and its minimum distance. So I'll explain you in this way. Like from any node, let's say, what we can say,
0
okay,
to 1.
So indexes are as like this, 0, 1, 2, 3, 4 and all things, right? So what I'm taking is that what is the node? This is also a spanning tree. Okay. What is the node that is at least a distance from the source right now? So what I'm doing is I'm going in a greedy way that first I'll start iterating 2 from 0. Why? Because it is at a least distance. I'll not start iterating 1. So understand it in this way. Let's say if the 0 is completed, let's say, then which is the next node to do? The next node to do is with the least distance based upon my spanning tree, and that is 2. So for that, I'm getting this index in U in my code. And then what I do in my graph, what are the edges between U and V? That I'm finding U and V in the sense this V are all. V is all, like V1, V2, V3 you can say. And then I'll update the distances of this all three, and I'll find the distances as graph of UV, because my graph is defined as adjacency matrix, as I said, so that I can get the weight of that graph in order of 1. Got
Sure.
it?
Got
Yeah.
it.
So I've got the first node which I have to start traversing. Okay, I have marked the spanning. So instead of spanning tree, you can consider it as a visited nodes as well, just a visited one, and that uh, just for the true and false. And the parent-child relationship is with a spanning tree. Okay, is with a spanning tree. Now, not spanning tree, visited one. Now, if this U, obviously first time when the first distance, first node I'll find it out to traverse, it will be unvisited. So I'll mark it as visited. And what I'll do, all the children, all the nodes which are having the link of graph from U to V, that means U to V there is a age. As I said, U to V there is an age. So for all the nodes, I'll find it out. If there is an age, then I'll find it out the distance. And how? Graph of UV, that is the age value. Graph of UV, that is the age value. And distance of U, so far whatever the distance I have found it out of U, let's say initially whatever I have found it out, right? So let's say if I'm starting from 2, 2's distance was 3. So let's say this is U. So its distance is 3. 3 plus for all the nodes of graph. If it is less than already existing, then I'll update it. So the same thing I'm doing, but the finding the next node is tricky. Finding the next node is that I'm finding with the minimum distance. Minimum distance is like this, that from 0 to 2 is the least distance from 0. So that's why I have taken 2. Now once I update all, my next node will be with the least distance from source, which was 1. Why? Because rest of the nodes, like let's say 3, can be reachable via how much? 3 plus 4, 7, or 4 can be reachable via 3 plus 3, 6. So what is the minimum distance from source? The minimum distance from source after 2 is 1, which is having a distance 4. So then I'll start updating distances 4 so that I don't have to use Q. I iterate over all the nodes based upon its distance from the source, so that I don't have to use Q. Otherwise I can use the Q as well, so that I just keep on updating all the children. Okay, instead of that, the implementation is in terms of being a little bit greedy, that rather than going into getting all the children's and updating all the ages, I'll go and I'll find it out whatever the least distance from the source is, and I'll go and update for all. So just the implementation of that is with a greedy rather than all the children.
So, Dhaval, in that for int v equal to 0, v less than v. So in our case, if we are traversing for the second node, so here we will get
All the nodes,
all the
5
nodes
as
of
well. You are telling about the 5 as well, right? Or 5, or whichever is not in connection of 2 as well, right?
So we will be getting all the two children, two connections, right? Like 1, 3, and 4. We will be getting as part of in that for int v equal to 0.
No, we will get all. Like for 2, we will get all 0, 1, 3, 4, and 5. So we will iterate over the all. If you see, v is number of vertices. It will iterate over all. But
Okay.
we will find the age for only few, which is 220, 221, 223, 224, not for 225 as well.
Okay.
Now, 222 age is not there. So that is also not, what you can say, not to consider. But 220 not to consider. Why? Because 0 is already visited. If you see, whenever I mark in a code, I mark it as visited, not a spanning tree, visited one. So that is visited, so we'll not consider 220.
Okay.
And 221 will consider because there is an age. 222 no age. 223 there is age. 224 there is age. 225 it will come into this loop, but in graph 225 there is no age. So that's why if it is not 0, directly will discard it. So
Makes
yes, in a loop everything will come, but we are considering only for the children, so that I don't have to, so the code I have written in such a simple way, such that we do not go into unnecessary all the details, like who are the exactly children of 2. Rather than finding out who are the exactly children of 2, let's go for all.
sure. Makes sense.
Right. So that unnecessary coding complexity, we do not add it. Otherwise, we will have to use adjacency list over here, though we are using adjacency matrix, right? So instead of doing that, easily I have done it like this, that go for all. If it has an age, that means it's in a children of that or the connection of that. If it doesn't have, no worries. Got it? So in this way, we'll keep on updating it. And if you see what I have updated, okay, if it's not visited, the age exists, and distance u, final distance, is not equal to maximum value infinite, okay, and distance of u, the final distance from u plus graph, is less than already existing. In that case only we are updating it. Okay, so all the conditions I have written into one case, that from 2 to wherever we are going, let's say 2 to 0, it's already not visited, do not consider it. Whatever the new distance I'm finding from 2 to 1, if it is not minimum or lesser than already kept into distance, all that conditions we have kept it into that. And once it is done, with a simple function print solution, I can print the minimum path, which is, as I have explained, that 7 or the 5 can be reachable with a 7 distance via node 3. 3 can be reachable with 6 distance via node 1, and 1 can be reachable with 0, and it is a source. So in that way we can find it out. For source to destination, simple, shortest distance. Clear? Now if you see here, we are getting only shortest distance between any two nodes. The similar kind of algorithm, shortest distance algorithm, we have seen for 2D metrics. Do you think that similar algorithm can be applied over here? Because if you see, 2D graph is represented with 2D metrics. Now, can we think of that logic of DP over here, and we see that what will be the benefit we are getting over here? If it can be solved with DP, why we are solving with, say, with some other example or with some other logic? Can you guys think about it? What is the benefit that we will get over here? And what is the benefit that we won't get over there? Or what is the benefit that we will get with the minimum distance algorithm of the DP?
Dhaval, are you talking about minimum cost path?
Yeah, minimum cost path. It's the same thing, right?
Mhm.
So if you see the final implementation, then probably you'll get the idea. The first benefit over here would be complexity, obviously. The benefit or the cons, I would say pros and cons if we are discussing. The con over here is that we have just a minimum distance from source to destination. Like in previous approach, minimum cost path, we can change it for any source to any destination as well. But over here, no. Over here, we cannot. Over here, it's only for source to destination. Now let's think about what is the complexity for this code or the logic, if I say. So if you see very simply, we are iterating over all the nodes, and in that also we are iterating over all the nodes again. If it has graph or if it has the age or not, based upon that, we are taking a decision. But in a worst case, all the nodes we are traversing twice in the sense like all the nodes from V1 to Vn we will traverse over here, and for all V1 to Vn again we will traverse from V1 to Vn. That is what complexity, order of V square. Isn't it the same as previous algorithm that we have seen of minimum cost path? Yeah. So what would be the benefit over here? Right now, nothing. Right now, nothing, because the way we have implemented it. Now, if we change the implementation, probably we can get the lesser complexity. Probably. Think about it. That how can we get the lesser complexity over here? What is the main cause of complexity over here? The main complexity which is creating is finding a minimum distance and iterating over all the graph rather than all the nodes, rather than only the children. So now if I iterate over only the children, my complexity will be lesser. That is first thing. Second thing is that finding a minimum distance node, the next node which I have to traverse, which can be least from the source, that is also adding extra complexity. Now, if I implement or if I reduce the complexity of this both, my complexity can be reduced. What is the way to get this one easily?
Well, can you please tell me one more time why is time complexity is O of V square?
Okay, so it is just like this, that this count is going for what? All V's, all the nodes. V is number of nodes, right? So I'm iterating over all the nodes and I'm finding the minimum distance node from the source every time. Because I'm going greedy rather than going for all the nodes or all the children of any node, what I'm doing is whichever is the minimum distance from the source, I'll just iterate over that only. So the point is for V times or the number of nodes n times, anything you consider, either V or n, that much time I'll get the minimum distance node. And for that node, I'll iterate over all the nodes and I'll find it out whether there is an age or not. As I said, the logic will be something like this, that once I found out from that, the next node that I have to traverse is 2, because that is the least distance node. From 0 to 1 I can reach into 4, and 0 to 2 I can reach into 3, which is the next node that I have to pick up. I have to pick up with the least age, 3. So that is U. Okay. After that, what I'm traversing on all the nodes 0, 1, 2, 3, 4, and 5, and I see whether it's unvisited, whether the age exists, and the final distance is lesser than what it has already, then only then update it. So the point is, for each node I'm iterating over all the nodes again and again, and that's why it's V into V, which is V square, or number of nodes n, then n square. Clear?
Yes,
What?
Dhaval.
Obviously, because this thing will also give us more complexity, like I'll iterate, so it will be like into plus only, that for all the nodes I'll iterate over this once, so it will be plus v only, or n square plus n only, n square plus n on v square plus v. But the point is, this both is adding the extra complexity. So how can I reduce this extra complexity if I have to implement it with a different way? If I can implement it with a different way, how can I reduce the complexity? So to find out the minimum distance, what we do, this distance array we traverse and we find it out that which is the least. So far, let's say over here it was 3 and 6 only. Yeah, 4 and 3 only. So I iterate over a whole array of this distance and I found it out which is the least distance after 0, which is the least distance from the source, 3. So then I'll start pick upping this. So that minimum distance also is, this logic also giving me the complexity of order of n every time. So that is also resulting me into extra complexity. So if I do not do these both operations, then I can have lesser complexity. So this I can reduce with heap so that I can get always the minimum distance at the top. How? That we will see. Second thing is that even if the graph is implemented with the 2D metrics, as I said, if I implement somehow whole graph with adjacency list, and if I start processing, I do not have to iterate over all. I can just iterate over just the children. Then I can have lesser complexity. Correct? Then what I have to do for all the nodes, this I can get, this operation I can get in order of 1, and this can be into order of ages, right? All the ages, in the sense whatever the maximum number of age that 2 has, 2 to 1, 2 to 3, 2 to 4. In worst case it will be all the ages. So finally, in worst case, I will have order of v plus e log e. E log e. Why e log e? Because the age I'm keeping into the heap. All the age I'm keeping into the heap. Correct. So in this way, I can get in lesser if I implement it with the help of heap and adjacency list. So let's see, can we change our coding instead of adjacency metrics to that, and we can understand that how can we reduce the complexity of this code. Clear?
Yes, sir. Now, just before that, can you actually that ideal link that is very, it is not visible.
Sorry?
The ideal link that is given at the
I'll put it into the thing, but otherwise I'll just write it down. This whole idea one slash E6E, just a minute, was, I remember, it's E6 4F8U. I just reduce the E.
is visible now.
Yeah. Yeah.
It's visible.
Now let's think, how can we implement with the heap? What do I have to do so that I can initialize the heap such a way for all the nodes and all the things? How can we define the heap node? That is one thing. And second thing is that how can I define the vertices? Oh, sorry, the graph with the help of adjacency list. So first, or we can stop over here and we can see the heap implementation later on. But we can understand it in a simplistic way, that what do we need from heap? We need that what is the next node to pick up, because I want to go for greedy approach. Rather than iterating over all the children, to reduce the complexity, I just want to iterate over the children whose distance is least from the source. So to do that, I have to implement it with the heap. So how can I implement a heap node? So the heap node will have two major necessary thing, which is what is the index of that node? So let's say heap node is something h. So the heap node will have what? The index value of that node, because that node's value will be something like this 0, 1, 2, 3, 4. So to identify that node, that index value should be there into heap, right? Or like a data, as I said, the definition of a node. So that thing we need. What is the else part we need? The else part is that distance, and that distance is from source, and this will be keep on updating, because if
So
you see, yeah,
like, is it like each vertex will have its own heap?
no, each vertex will not have heap. What we will have, consider it something like this, that initially when the heap is empty and I'm just adding the node 0 into that, consider like that, okay? So then I'll have this just one definition of that, that the node is definition is 0, and it can be reachable via source in 0 distance. Now once I iterate both the children, what I'll add into the heap is that the definition of a node, or the index of the node, is 1 and the index of the node is 2, and they both can be reachable from the source in how much distance? That is, 1 can be reachable with 4 and 2 can be reachable with 3. That's it. Now I'll remove this node from the heap. So heap will have which one on top? This one, because the heap's definition is that it sorts based upon the source to this node's distance. So on top, which, or the priority queue, what I will have into top, this node, I'll pick up that and I'll start iterating that first. Once I do that, let's say I iterate all, and once I update it, what I'll update, if the same node is already present into the heap, let's say if it would have been 6, it would have been 6, right? Then I'll update it that, okay, no, 1 is reachable via 4 unit with some other node like myself 2. Next, 3 is reachable with 3 plus 4, 7 unit, and 4 is reachable with 3 plus 3, 6. Now this all nodes are there into heap. I'll remove this because it has been processed. Which is the least distance next? The next least distance is 4. Now I'll start iterating over the 4. So either I can have heap, or in simple terms, I have the priority queue with the definitions like this. Oh, in previous slide we have the priority queue with comparable method, that which one to compare, the heap node or the node dot distance. So either you can create a user defined heap, or you can create a priority queue as well, as I say, right? Then the implementation part will be taken up. But so far, with a heap or priority queue, we are keeping from source distance to that node. Is that clear? Because that is the main thing which we are extracting from here. That is giving us order of n extra complexity. Next order of n square, which is giving us extra complexity, n into extra complexity, which is giving us this, is order of n square. So we'll see for that how can we reduce that. So as I said, that we can have the extra complexity because of going on over all the nodes. Instead of that, whatever the node I get it from here, u, and all the adjacency list of that, if I iterate, then I can have lesser complexity. So we'll see that. So first let's define what is the heap, what is what you can say, the implementation or initialization of heap, what are the things that we are inserting into the heap for initial thing, and how we are fetching this part and this part, we'll see just in next slides. So let's see, I have defined my heap as this. Heap node is equal to new heap of all the vertices. Definition I have given. Initially, for all vertices, the distance is infinite, and the vertex ID or the vertex is the ID of that, whatever the I is there. So right now, I would say the heap is empty. All the nodes are there with the distance infinite. Now, heap node for the source vertex has distance 0. That is to be understood. So that the first node that I'll start iterating over it, it will be source. Perfect. Next thing is that I have to start iterating over the graph. And before that, once the heap is defined, mean heap is defined, this whole all heap nodes I'm adding into the, or the nodes of heap that I'm adding into the mean heap. So that on a top I'll have the source vertex. I would say like this, 0 can be reachable with 0. Rest of the nodes are with 1, 2, 3, all the indexes are with infinite. So somewhere they will be into heap, somewhere, whatever the logic will be, but the mean heap will have this on the top. So that first I'll start iterating this. And then once I extract this node, what I have to do, I'll find it out that 0 is the node that I'm operating on it, and all the adjacency list 0 has. I'll iterate over all. Whatever its children are, or whatever its node I have found, its distance I'll update it into respective heap nodes. And so I have used the array of heap nodes so that directly I can go to that node. If you see something like this, let's say heap node I have created like this: 1 with infinite, 0 with 0, let's say 2 with infinite, then 3 with infinite, then 4 with infinite, and then another children is 5 with infinite. Now 0's children are 1 and 2 in the graph. In the graph, 0's children are 1 and 2. Now once I update the distance of this, how can I directly go to this node rather than iterating over the heap? How can I directly go into that and update it? So to do so, what I have kept is array of all the nodes. So let's say this is one node, another node, and these are all the objects. What I have kept, like 0, 0, the soft link to this, 1, 0, the soft link to this in the same indexes, 0, 1.
Well, this is the structure of heap nodes, right?
Yeah, this is the structure of a heap node, and the heap nodes array also I have kept. So why I have kept the array of heap nodes, that reason I'm giving, so
Okay.
that I can directly access. So let's say once new distance is, let's say 4, so I'll update it over here 4. I'll go to the value 1, I'll update it to 4, so that directly I'll update it to 4. Then heapification will happen, because the definition of a heap is comparator is based upon the distance value. So then heapification will happen. Got it? So that's why I have used this extra array to go to that node easily in order of 1 and update that value. And in heap, all the vertices or all the nodes I have added. So this is the definition of a node and rest of the things. Clear? Now, the next part, how do we process it? So the processing will be the same thing. Until the mean heap is empty, I'll fetch first the first node. That will be, let's say, source node. First, I'll get its vertex. I'll say that, okay, it has already been traversed. And then what I'll do, iterate over its all children. Iterate over its all children, update the distance. Now update the distance I'll do in two places. One is heap and another is spanning tree. Two places or a distance tree, whatever, wherever. There I'll update the distance. So let's see that. First I found it out whatever the vertex is, which has been got from the heap, and I'll get all of its children, adjacency list, and I'll iterate it over all the children. Now, first I get the age as an object, and then what I find it out is that if that destination is not visited, then only then I update the new distance with this, that the current key is a new distance. Okay, so like this, heap node of extracted vertex, whatever the extracted vertex, dot distance plus the age of weight. So let's say something like this: 0 is reachable via 0 plus 1 so far was reachable via infinite, and I have marked everything with 0. So that I'm adding plus the age weight. So age weight is 4. So 1 is reachable with 4. So this thing I'm updating over here. This thing I'm updating over here. If the older value, this is the new value and this is the older value. If new value of the age is lesser than that, then only then I am updating into heap and in the heap node as well. So heapification will happen and the heap node of the array and then node that I'll update. And at the end, for all the nodes, if it does complete, like if loop and if and for loop, everything, and at the end while loop, then if I just print the Dijkstra of from the source vertex, then I can print it. But which all nodes or which all the graphs will be there into, or which all the edges will be there into Dijkstra. Got it?
So, one question, like both heap nodes and the min heap contain the same structure, right?
So it is something like this. I'll tell you. In a binary tree, node definition is what? Data, left a tree, and right subtree. And that this structure defines the tree. Now, over here, what is that? That this structure is part of, this node is part of heap. This node is heap node. Got it?
Yes.
And that heap node, I have kept it into array as well, so that I can go to this heap node directly. So let's say heap node's index is 0. So in array of 0, this node structure or the object of or the reference of that node also I have kept it, so that I can go directly and update it. As I said, or as I explained it over here, that this object and this object, they both are same, but they are stored into this 0, 1, 2 array as well. So that whenever I say that 0's children is 1 and 2 and I update its distances, what will happen is I'll directly go to its index value and in heap I can directly update it. Got it?
But generally that is the general implementation of heap as well, right?
Yeah, that is the
No.
general implementation of heap. Yes.
Okay, so if we are storing the in the array format in the heap node, the heap nodes array, what is that min heap object that we are having?
Oh, got it. Got it. Got it. Got it. I understood the difference between those. Got it. So over here, the children parent relationship in mean heap object will be different than over here. See, over here, the indexes will be based upon its indexes into the graph. Got it? Right? While over here into mean heap, the parent-child relationship will be based upon the distance. So the zero's next children will be 2 and 2's next children will be what? I'll tell you. Let's say if it would have been 6, then 2's children in mean heap will be something like this. 0's children is 2 and 2's children in mean heap. What you remember the array indexing structure, right? In which way? The 2's children will be 3 in mean heap. The next node. Getting my point? Because over here, we are keeping it in order based upon the distance from the source. Got it? So that's why
Yes,
in
yes,
mean
sir.
heap, the indexing will be different. And over here, I want to keep it in the same order of the graph indexing, like 0, 1, 2, 3. That's why. So that's why I have kept two different structures. One is mean heap, another is this one. Clear?
Yes, Dhaval.
Yeah. Now, with the help of heap node or this structure, how can I print the Dijkstra's code? So we can directly just update one value into heap node, and we can print this whole thing, or whatever the shortest path we will have from source to destination easily. And that is, what is the parent of any node, so that we can update it very easily over here. That for any node, any extracted node, let's say this is the extracted vertex, right, which is the least distance for all its children into adjacency list that we get. And whenever we get the list one, I update into adjacency, oh sorry, a heap node as the parent node as well. So something like this, that in this array of heap nodes, if I have this kind of definition that 0 is reachable with 0 distance, 1 is reachable via 2 with 4 distance, 2 is reachable via 0 with 3 distance, then I can have this whole path that to reach to 1 you have to go via 2, and 2 can be reachable with 0, isn't it? So if I just update these values, I can get it printing, because this value is something like this: who is the parent of which node, or who is reachable via which. So if I get that quickly into the same objects, then I can print easily this minimum spanning tree. I won't say minimum spanning tree, but it is a spanning tree from source to destination with the minimum path, minimum distance path. Clear? Because that thing we can directly keep it into this. Who is the vertex? What is the vertex? Based upon that, I can do that. Instead of vertex and distance, I can also keep one more parameter as parent, and I keep on updating that who is the zero's parent, 0, who is the one's parent, 2, 2's parent is 0, like that, and so on. We'll complete it. So in what we can say, this printing this heap nodes structure will be useful if I also update the same thing, parent-child relationship. Clear? I'll just explain the next question and then we'll rest our class today, and that is topological sorting. Okay, this brings that we will take up later, or you guys can figure it out how we can print it. It's fine. So what is topological sorting? Topological sorting is just like our workflow operations, or I would say after which node can be executed. Like once 0 is done, then only then I should be able to execute 3 and 2. And to execute 3, there should be that 0 is completed and 2 should also be completed. So like that, if you have the dependencies, how can you process all the nodes, or what is the order of the nodes processing? Like what is the order of this nodes processing? The order of nodes processing can be 0, then afterwards I can complete 2, then afterwards I can complete 3, then I can complete 1, then I can complete, even if I don't complete 1, I can complete 6, and I can complete 5, then I can complete 1, then I can complete 4. Or 0, 1 I can complete first, then 2, then 4, then 3, then 5, then 6, something like that, right? Based upon the relationship over here. To complete 5, you need to have complete 2 first, and to complete 6, you need to have complete 3, 2, and 5 first. So based upon that. So point is, how can I find it out, this ordering? That is called a question of topological sorting. Once we'll understand this, we'll see that where in interview question it can be asked. As I said, there is one question of alien dictionary that can be, I think that can be done with this also. Then there is chaining problem, and there are few interview questions which can be asked, but the beneath logic of all of those, just like we have seen in LIS, that there are multiple questions can be asked with LIS, but the beneath implementation of LIS is just one. The same way there can be multiple questions which can be formed on top of this logical question of topological sort, and that too will take some proportionate of the traditional algorithm that we have seen so far. Okay, so we'll see this question next time. By that time you guys can go through the videos again and see the printing of this whole and implementation of this whole Dijkstras and Prims and Kruskals. Okay, there are many other algorithms as well, but they are not much important into interview, so we are not taking all. Rather than once the primitive algorithms which are necessary are complete, then we can directly see the interview questions. Okay, so from the next session, I think in next session, can we have the session? Can we have the next session directly on Saturday?
Sure,
And
sure, Dhaval.
Saturday we'll try to go for this topological sort. And once the topological sort is complete, we can see how the same question can be into alien dictionary can be asked in next session. Then we can see the graph coloring problem, and we can find it out the cycle, and we can also find it out the bipartite graph. Bipartite in the sense, I won't say graph coloring and bipartite will be the similar one. We'll see that. But once we find it out the cycle, what question I have thought was how to find it out the bridge into that. Yes, I have said bridge. So in next session, we'll try to cover all of these questions. Okay, we'll try to cover all of these questions, and each of them are very much related with whatever we have seen so far. So before next session, just have a little bit clear understanding of all the graph topics and adjacency matrix, adjacency list and its implementation, how the way we have used heap and all that things in this. Okay, so we'll meet next session and we'll see many of the interview questions which are so far I have seen being asked into the interviews.